Hope all of us are doing fine. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In this particular video, we're going to look at the second bit of representing an ideal gas of diatomic molecule in terms of a partition function. And in this case, we will be considering the three specific degrees of freedom for translation, and 2 for rotation, and 1 for vibration components of this kind of a molecule. Now, in this case, I had mentioned, of course, from our previous video that the rotational properties of this particular diatomic molecule are going to be determined by 2 specific aspects, and those were the moment of inertia and the distance from the center of mass. Now, in trying to obtain the allowed energies of this specific rotational, freely rotating molecule, we have said that we are going to use a Schrodinger's equation, of course, in trying to obtain this particular allowed energies, which was given in terms of this specific representation. And we have said basically that this is going to represent a rotational constant, which is given as the ratio between Planck's constant and the square of pi and the moment of inertia given as such. And of course, we had said that this J is going to be the rotational quantum number, which is going to be represented by values of starting from 1 to positive infinity given as such. So the relationship between for this value of J and B, of course, can be described using the rotational energy level diagram for a diatomic molecule, which I've given in this specific case, representing the various values of B and G given as such. Now, I mentioned that basically we can obtain this specific value for G, which is going to be given as 2J plus 1 given as such, whereby this G is going to represent a degeneracy, and then J is a rotational quantum number, and therefore this is going to create a relationship between the component of G, J, and B, and that of course is going to explain the specific energy level diagram which I've put on my right. Now, in this case, we're going to look at a specific aspect, of course, of trying to express this particular equation for the partition function by taking the rotational contribution of a specific diatomic molecule. And in this case, I'm going to use the partition function, which we had used, of course, in trying to represent a particular state of energy for the rotational component. So in this case, this was given in terms of Q, as given as the summation from V. Now, in this V, we had used it in our first video in trying to describe a specific state of perhaps a monoatomic or a diatomic molecule. And of course, we had considered that various the description of energy of that very specific state for the electronic, of course, rotational, vibration, and translation aspect in that particular case. So this was given as an exponent of negative B and this particular component of energy, which is a rotational component. And this, of course, gave us a general description for trying to give a rotational contribution of this specific energies of a diatomic molecule. Now, for us to obtain the expression for the partition function, we're going to have these specific energies summed up over this particular, of course, range. And I'm going to show this one perhaps in trying to give it in terms of an illustration. And this is going to be multiplied by the various degeneracies which I've given in terms of G. So we're going to have this expression being represented as the translation partition function is equivalent to the summation of energies. So in this case, if we're going to consider the degeneracies, then we're going to look at the first one. And of course, we're going to consider the non-degenerate. This is going to be the non-degenerate states, and of course this is going to be multiplied, as we said, by the degeneracies given as Gi, and this is going to be given as the exponent of a negative beta u, which is a rotational component of these particular energies. So this is going to be assisting us obtain the expression for the partition function. And of course, this is going to be given in terms of this specific representation. Now, this equation can be given by trying to consider the Schrodinger's equation for a representation of the allowed energies, which we are given in terms of UJR is equivalent to BJ into J plus 1. And of course, also considering the aspect of the rotational constant, which are given in terms of B. whereby I said P can be represented as a ratio between the square of Planck's constant and 8 pi squared times the moment of inertia given as such. So in this case, we are going to do a substitution by trying to have this specific representation for energy for the values of j from 0. I said j can assume values from 0 to infinity. So therefore, for the rotational partition function, this is going to be given in terms of the summation of values of j from 0 to infinity. And then we're going to have this one substituted for g. So I decided basically that this g is going to be represented, or the degeneracy is going to be represented by 2j plus 1. And therefore, we're going to have this specific substitution given by the values of 2j plus 1. And then we're going to multiply that one together with the exponent over this specific energy. So we're going to have this specific, of course, representation for the values of B, whereby we're going to have this B substituted, or this energy substituted for this particular component, and the B which we have represented using this rotational constant, of course, is going also to be expressed in this particular representation. So therefore, this is going to be an expanded equation representing the value of B and uj for this particular energy. And also we shall have this specific beta. So there's a difference between this representation for beta which I've given, and also the value of the rotational constant which is going to be given as, of course, this particular value which I've given as such. So as well, we are going to do a representation for this beta, and of course, as we are going to give this value for the Schrodinger's equation for representation of allowed energies, we're going to do a substitution as well and include those components. So we're going to have this one represented as negative j into j plus 1. And then we're going to have this part of the rotational constant of the h squared given as such, as our, of course, a numerator. And then we're going to have this specific component of 8 pi squared as our denominator, forming this specific aspect of the representation for that. And then we shall have kbt representing the beta. So this is going to be kbt representing the beta which has been given at this specific point. And therefore, that's going to be in terms of 8 pi squared I kbt given as such. And all of this is going to be the exponent of that specific value. Now, in this case, we're going to look at a specific aspect, sorry for that, which I said is referred to as a rotational temperature, which we're going to consider in this particular case. Now, the aspect of rotational temperature is going to be taking account of the specific, of course, units of the Kelvin scale, and whereby we're going to have this particular rotational temperature as a representation of theta r, theta sub r, and that is going to represent the values of the ratio between Planck's constant and the value of 8 pi squared I kb, and of course that's going to exclude the component of t given as such. So if we try to look at this specific aspect, of course we can do a substitution for this rotational temperature, as we're going to see, excluding this specific factor of j, we're going to see that the numerator in this case of h squared is being represented, and then we're going to have 8 pi I kb excluding t in this particular case. Therefore, we can write this particular equation perhaps in let me just check. So I'm going to do away with this so that we can have a space. So we're going to write this equation in terms of the rotational temperature, which is going to give us an equation of the form of the Q rotational, or the rotational partition function given as the summation of values of j from 0 to infinity, and this is going to be given as 2j plus 1 for the degeneracy, and then multiplied by the exponent of the negative value of j into j plus 1, which is basically this specific component. And then we shall have this one, of course, all over t. Remember, when we were substituting for the rotational temperature, there was a component of t, which is the Kelvin absolute scale, which is being given, or temperature, which is being given in terms of t. And then we're going to have that one multiplied by the rotational temperature given as such. So this is going to be perhaps just reserve it there. So let's have this one given as such. So this is going to be multiplied by the rotational temperature, and this is going to yield this specific form of an equation, which is going to include the component of the rotational temperature. Now in this case, we can use this rotational temperature in trying to describe various aspects of the molecule, and therefore it's going to assist us in trying to describe the classical behavior and the quantum behavior of this specific molecule. Now, in my subsequent discussion, I'm going to look at some of the ways in which we can evaluate this specific equation, perhaps in trying to consider the summation and, of course, the integral part of this equation in trying to describe various aspects of the quantum behavior and the classical behavior of such a kind of a molecule using the rotational partition function. So that is it for now, guys. But kindly check our description boxes for various links of other videos which are going to assist us, of course, have a fully comprehensive aspect of this concept of the partition function for a diatomic molecule. So that is it for now, guys. By God bless you. Catch us in our next video.